Hi, we're Team 1120 and we're doing Problem A, Kangaroo Care, for the SCUDEM modeling competition. We're from the University of Maryland and our members are Adam, Brooke, and myself, Katherine. Our task is to develop a model of the interactions between an infant kangaroo and its mother or human baby and its mother under a kangaroo mother care treatment. For our group, we decided to model the interaction of human infants and their mother with a KMC treatment. KMC is defined as a treatment for preterm infants that is skin-to-skin contact of the mother and the infant. So we're going to assume these conditions. We're going to limit the infants to be born in a hospital setting and those that are from first world countries. Specifically, we looked at premature and low birth weight infants, as KMC is specifically geared towards these groups. We assumed that the interactions of skin-to-skin contact of the mother and infant would be periodic. We omitted any external factors such as risk of infection or possibility of disease. And finally, that all infants would have the same rate of mortality. These are the most important factors we looked at that affected the mortality rate of the infants. First, the early initiation of kangaroo mother care is within 24 hours of birth, and we saw that an early initiation of contact would greatly decrease the effect of mortality than a later initiation after 24 hours. Another factor is going to be how long the infant and mother is within skin-to-skin contact. This is going to be measured in hours per day, and 8 hours is going to yield the most benefits than a lesser time. Here we have a quick overview or general idea of what our model is going to be. To model the mortality, we saw that the change in mortality equals some mortality in no contact minus the effect of contact on mortality. To break this down, basically, we have some base mortality, and depending on the level of contact or amount, duration, and the factors that we listed in the previous slide, this would change the mortality rate. So we have that the effect of contact on mortality is going to equal the rate at which some effect decays times actual period of contact. The rate at which effect decays is going to be the onset of KMC, so that is going to be initiation time, and then the actual period of contact is going to be just the duration of contact. So here we have the differential equation that is our model. We have M being the mortality of an infant. B variable is mortality in a no contact model. So we could say that's the base rate of mortality. Then we have F being some weighting function that describes some effect of contact on mortality. C is just going to be our periodic contact function over time. Finally, we have that time is measured in hours.
To determine our functions, we used a variety of curve fitting techniques on existing data. In particular, for the B function, which is the base mortality rate of preterm infants, we used data from Servano et al.'s predictive modeling on infant mortality and fitted an exponential curve to data representing the deaths of preterm infants by day, which looks about exponential. Then we normalized by the integral of the data to get a function of the mortality rate of preterm birth infants over time. We did this because we were unable to find the total amount of infants whose data were collected in the sample. Finally, we derived the differential equation from this curve with the initial condition 0.8 to yield the function b. For our contact function, we wanted a function that would vary between the values 0 and 1, which would correspond with either no contact or contact made at any time. We also wanted a function that would have a consistent period, and the first function we thought about was a sinusoidal function. Modifying the sinusoidal function to stay longer at each extrema, we ended up with this contact function, a function of the form 1 over 1 plus e to the sine t. This function is nice in that it is continuous and periodic. Finally, let us discuss our function f, which is the weighting function for the effect of contact on the mortality rate. From the paper, Kangaroo Mother Care for Preterm or Low Birth Weight Infants, a Systematic Review and Meta-Analysis. We saw that earlier KMC reduces risk and mortality by 33% compared to late KMC, and late KMC reduces mortality by 32% over 28 days. From this, we inferred that early KMC reduces mortality by 42.5% over 28 days. The paper also notes that the optimal contact period is over 8 hours each day. We found that the average initiation time used by each study in this paper for early KMC was at about 10 hours after birth, while late KMC was initiated at about 58.65 hours after birth. We used all this information and split up the percentages of reduction by each type of KMC over the 28-day period. We also assumed that the full reduction would be attained if contact was given for at least 8 hours a day. Finally, we fit this curve using the asymmetric sigmoidal method and yielded a function of the form 1 over 1 plus t squared. Using MATLAB and ODE 45, we plotted trajectories for our mortality rate over 28 days. We graphed the blue function, which represents mortality in the presence of no contact, and the green function, mortality in the presence of constant contact, to confirm that varied contact will stay bounded between these two functions. As expected, the red and orange functions seen here, which represent mortality with varied contact, stay bounded between these two curves. Recall that our contact functions model with the sinusoidal-like function with specifically the function sign in our exponent shown here. We wanted to determine what would happen to the mortality rate if contact was started earlier or later. The orange line shown here is modeled with the function sign in the exponent, while the red function is modeled with the function cosine in the exponent instead. This means the orange line corresponds with contact starting immediately after birth, while the red line has contact starting a little bit after birth. Since we have changed no other parameters in our contact function or the rest of our differential equation, we know that the periodicity of contact will remain the same. As seen here, just changing our contact to start at an earlier time is projected to decrease mortality more than later contact, even if contact is made at the same frequency and all at the same intervals.
Our formulation model means that we can replace the contact function easily. For example, instead of using a continuous and smooth contact function, we can use something which more closely resembles a real KMC procedure. This contact function is piecewise with 3 parameters: I, indicating when contact starts, P, indicating how many hours per day the contact is made, and K, which is how many cycles of contact are done before the regime is stopped. Furthermore, since the previous f of t function didn't show large differences between the different KMC conditions as we expected, we also tried a different approach. Sivanandan et al.'s paper shows how different contact conditions can change the mortality rate. For example, the early initiation group had an 80% lower mortality rate in the first 28 days than the late initiation group. We can simulate these conditions by changing the contact function parameters. We can then approximate mortality with the integral of the mortality function from t equals 0 to 28, and then change the f of t function in order to match these values as closely as possible. The values of I and p were chosen as to reflect the median values within each group, as shown in the paper. We did a systematic search of the constants for the chosen form of the f function, and found that the function shown here was the best fit. In other words, it minimized the difference in the expected and actual ratios between the experimental groups. The expected mortality ratios using this function are shown in the tables on the right. Here are the output curves for the experimental groups just mentioned. For example, on the graph on the left, the purple and green lines are overlaid on top of each other. This indicates that the group which had very high contact levels per day had essentially the same mortality rates as the group which had constant contact. If we plot the area under the curve for various values of p and I, we'll see a downward trend in the mortality as p increases, with the greatest drop happening around p equals 0.4. In contrast, the effect of the initiation time on mortality is considerably less consistent, though it's clear that one should initiate as early as possible in order to maximize the reduction in mortality. In addition, with this formulation of the contact function, we can easily add another parameter s, indicating that the KMC is paused every sth day. Fixing I and p to some values and trying out various values for s, we can see that the parent skips KMC every 5th day or greater. The reduction in mortality is less than 0.5%. Our model indicates that the early stages of KMC are the most critical, thus it's important to begin the procedure as soon as possible. In addition, in order to minimize mortality, the contact should occur for at least 10 hours per day during the first period of the child's life. As mentioned in the problem statement, KMC requires more intense use of resources, like time and availability of practitioners, in order to ensure that the mother and infant are properly cared for. This can be more exhausting for the mother in the early stages of the infant's life. Our model indicates that the mother can take regular breaks in intervals of 5 days or more without compromising the health of their infant.
Questions that arise with our limitations of a model. So how could we measure or see the effects of KMC over a longer time scale? Well, instead, maybe we can improve our model by not modeling just only 28 days, but for a longer time frame. And another question would be, how could we make it so that the infant rate mortality does not end up at 1? because we relied on data for mortality rate, we assumed that the infant's mortality rate just ends up at 1. This is not going to be the most realistic, but also another limitation is going to be a large amount of variability. Our results just really depend on the parameters like f of t, the function, the weighting function that we chose. So we could try out more different functions for the parameters. We also might also incorporate the factors of infection into our model, so then it could be a more realistic scenario.